Okay, welcome everyone to our next installment of the Prague Homology Seminar. Our speaker today is Arman Taghavi-Chabert from Warsaw University, and he will talk about perturbations of Fefferman's conformal structures. So please go ahead.
Okay, so I would like to thank Igor for giving me the opportunity to talk here. So maybe I will switch off my my video so that it doesn't distract me so much. Okay. So I'll be talking about my very recent work. So it was meant to be out maybe this week, but I have to delay it a little bit. So it's based on a recent preprint. So I'll put archive. Then how does it work? Maybe 2302, maybe it will be 03. And so the main point of this work is to investigate the point of interaction. I mean, there are 2 points of interaction between CR geometry and conformal geometry. So 2 points of interaction between these two geometries. And one of them is quite well known. So it's the so-called Fefferman construction. So this is the first point of interaction, Fefferman's construction. And this harks back to 1976. And the point is, well, so you start with a CR manifold. So I will explain all this terminology later. So it's CR manifold of contact type, so it's non-degenerate. It has dimension 2m. And you can construct a conformal structure on a circle bundle over this CR manifold. So it's a canonical circle bundle. And this is done in a very canonical way. So the point is that you can relate CR invariance to conformal invariance via this construction. So a conformal structure, so an equivalence class of metrics that are conformally related. So this is quite well known, but there is something that is less well known, and so the motivation comes from general relativity. So the motivation is from GR. And especially the golden age of general relativity, where people were interested in the so-called algebraically special Lorentzian Einstein fourfold. So this works in 4 dimensions only. I mean, the high dimensional story is a little bit more complicated. So where in Fefferman's case you have a construction, here it's a description. So what are these algebraically special Lorentzian Einstein fourfolds? So they actually admit a foliation by a null geodesic, so a certain type of foliation. Okay. And the leaf space of this foliation turns out to be a CR manifold. So CR threefold. Okay, so here a lot of people were involved. So let me give you a few names. So I would say Robinson, Trautman, Kerr, Newman, Penrose, and many more. I'll mention more names later. So it all started then. I mean, the realization that you get a connection to CR geometry was made much later, especially by Penrose, but also by the Warsaw School. So, so the Warsaw School will be involved. So like Tachel, Lewandowski, Nurowski, and of course people from the Penrose School, so people from Oxford. Okay, so there have been these two stories for quite some time now, and my aim is to reconcile these two stories. So the aim is express. Okay, so if I call this 2 and this 1, I want to express these algebraically special solutions in terms of Fefferman, the Fefferman construction. And this leads actually, so it will not be the Fefferman construction directly, because in fact, if you take the Fefferman space dimension 4, then if it admits an Einstein metric, or almost Einstein metric, as I will explain later, then it has to be conformally flat. So something is going on there. So one has to make some changes to this conformal structure. Okay, so let me review CR geometry first. So my first point will be on CR geometry. So I will, although this talk is mostly on the 4-dimensional story or 3-dimensional story, I'll be quite general at the beginning, because actually one of the points of this construction is that it leads to more CR invariant differential equations that could be of interest. So there is, so I'll start with greater generality. So for me, a CR manifold, so it will consist of a triplet where M is a smooth manifold. So I would emphasize that it's a real manifold of dimension 2m plus 1. H is a rank 2m distribution. And J is a complex structure on H. So basically it means that J squared is equal to minus the identity on H. And this setting tells you that MHJ is an almost CR manifold. So the requirement that, so if you have this complex structure, you have a splitting of the complexification of the tangent bundle into the eigen, the complexification, so I should say, not the full tangent bundle, but the distribution H. So you take the complexification of H, then it splits into the eigenbundles of J. And if these eigenbundles are involutive, so it means that it's closed on the bracket of vector fields, then you call MHJ CR manifold. And actually this condition is completely trivial in dimension 3. Okay, so you could study these CR manifolds in a lot of generality. So maybe I should put some references. So if you want to learn more about these, so there is a book by, so I forgot how to spell this name, or Jakubowicz, rather. So this is a very good introduction to CR geometry. But of course, the topic comes from the early 20th century. So I should put the name of Poincaré, 1907. So Poincaré asked the following question: can you find a biholomorphic map that sends a real surface in C2 to another one? And in general, the answer is no. You can express, well, you can find some invariants. Sorry, where is my pen? Okay, some invariants to characterize the existence of such a biholomorphic map. So this was done by Cartan in, I guess, 1932. Okay, and then there are more names that I could add, and yes, so like Chern and Moser generalized the work by Cartan. Okay, so maybe I could give you some examples in case you're not familiar with this. So, so real hypersurfaces of well, in Cm+1 are examples of CR manifolds. So for instance, so if I put coordinates, let's say Z0, so these are the standard complex coordinates, Zm, then well, so an example is, so it's, for instance, if I take the imaginary part of Z0 is equal to 0, so this is simply a real slice, really a copy of R2m+1 in Cm+1. So this is a very trivial example. So it's a case, this is so-called totally degenerate CR structure. But then I could take also the sphere of dimension 2m+1, and this is a more interesting example, although still very simple. So you just express it by, well, maybe I can put this equation. So this is the standard model for non-degenerate, non-degenerate CR manifold. So this is degenerate, and this is, sorry, yes, degenerate, and this is non-degenerate. Okay. In fact, I will refer to a non-degenerate CR manifold as a contact CR manifold. So, so this talk, it really is about contact CR manifold. So we shall assume that H is contact. This means that the distribution H bracket generates the full tangent bundle. Now, so if I take, so if I choose a contact form, so this is a one form that annihilates H, then, well, so some known properties, I know that there exists a unique vector field. So it's supposed to be called the red vector field. So I'll call it L, such that L inserts non-trivially into the contact form. And if I insert it into the exterior derivative of this contact form, I get 0. So then I can choose, so I can find an adapted coframe or admissible coframe, adapted coframe. So theta alpha, theta bar, alpha bar. And here alpha runs from 1 to m. So such that, So if I take d theta, I get I H alpha beta, and this is a Hermitian matrix. And d theta alpha is equal to theta beta wedge gamma beta alpha plus a alpha beta bar theta wedge theta beta bar. So here, H alpha beta bar is the Levy form, can be identified with the Levy form of theta. And the gamma here is the one form of a connection. And this connection is called the Webster connection. And it's the unique connection that preserves theta and d theta. And so it has torsion in particular. So the Levy form is torsion already. And this guy here, A, is another bit of the torsion. So A alpha beta is symmetric, and this is called the Webster torsion. So here I can raise and lower the indices with this Levy form H. And of course, if I do this, I change the type of indices. So this is the Webster torsion. Okay.
Arman,
so this is yeah.
So the contact structure. So this is something that any non-degenerate CR manifold will have, or you're imposing extra conditions on your CR structure.
No. This is, I mean, non-degenerate is really the same as saying that H is contact. It's the same.
I see.
So,
okay.
Yeah.
Okay.
Yeah. This is this is different terminology.
Okay.
Actually, most people will say non-degenerate CR structure, but I say contact CR structure. Mm-hmm. But yeah, it's just a matter of style, I guess.
So just to understand, theta is your co-frame.
Yeah.
So it has these three components. So there's a regular one form, and then there are two.
Yeah. So this is the complex conjugate of the other. So basically.
Yeah. And the first theta, the one that has no index, like what does it mean?
So this is the contact form. So this is So okay. So maybe I should put it here. So this is a choice of contact form.
That is the contact form itself. Okay.
Yeah. So
okay, contact form then extended by to a coframe. I see.
Yeah. So this is adapted coframe. Yeah.
Right. Okay. Thank you.
Yeah. No problem. Okay. So maybe I should emphasize this. So this is the Levy form of theta, and this is the Webster connection. And of course, on an arbitrary CR manifold, you do not have a preferred contact form. And so if you rescale this theta here by some factor, you have a rescaling of the Levy form. So if you think of the Levy form as being a sub-Riemannian metric, okay, so if you assume that H is positive definite, so okay, maybe we can make this assumption, but we don't have to. So if you assume that H alpha beta is positive definite, then it defines a sub-Riemannian structure on H. So it's simply a bundle metric on H, sub-Riemannian structure on H. Now, okay, so as I said, if you pick a different contact form, theta at equal to E phi of E theta, then you get a conformal change of this metric, of this Levy form. So basically what you end up with is a subconformal structure on H, a conformal class of metrics defined by these Levy forms. And so, in fact, CR geometry or contact CR geometry is very much like CR geometry, conformal geometry. So, of course, if you have a change of contact form, you have a change. You have a change of Webster connection. And here I'm not going to give you the full formula, so I will put it in this shorthand form. Let me see, like this. So nabla is my Webster connection. So nabla had the new one, and this epsilon here is simply d phi, where phi is this guy here. Okay. And so if you want to compute CR invariance, it should be invariant under these changes. So having a connection, having this contact structure on the top of your CR manifold allows you to derive CR invariance. Okay, so I need to make an additional definition. So the canonical bundle. So this is simply the top form of the annihilator of H01. And so this is a line bundle. And in fact, you can introduce a notion of weights. I cannot, I'll have to be very quick because otherwise I will not have time. So this, you can assign a weight to this bundle. And it is given in this way, okay? So what does it mean? So you can actually define density bundles, complex density bundles. So they're denoted in this way. For each W prime in, I think it can be defined over C, but I can't quite remember exactly, but I know they have to satisfy this condition. So the interpretation of this density bundle is, well, so one interpretation is as the canonical bundle, and the other interpretation is the interpretation of E11. So if you take a real section, so take a real section of this bundle corresponds to, so there is a one-to-one correspondence between real sections of this bundle and contact forms on my manifold. Okay, so what is it good for? Well, so let me give you an example. So this is a well-known example. So, so if I take a section, so a real section of this bundle here, and you suppose that it satisfies this differential equation. Well, first of all, you can check that this equation is CR invariant. But if you find such a solution, it means that so the contact form associated to theta the red vector field associated to the contact form given by this theta is a transverse symmetry of the CR structure. Red vector field L is a transverse symmetry. So it means that if I take the Lie derivative of, well, let's say, well, any, oops, any section V of H10, then it lands in H10. This is what it means. So this is actually an example of a so-called BGG operator. So it's been studied by a number of people. So maybe I can put some names here. So for instance, Chapkova, I think in 2008. Actually, it might even go back earlier. And so actually this differential equation here, so it does not quite, so it is useful in a sense because you can start from any contact form, and so any Webster connection, and impose a differential connection, a differential equation on your density of weight 1,1. And if you find a solution to this equation, you know that it is CR invariant. So it does not depend on the choice of contact one. Okay. So what I've done is I used
a question.
Yep.
So BGG operators are usually associated to a geometry or one of these parabolic geometries. So which geometry is this BGG operator associated to?
Well, it's the geometry associated to CR, contact CR geometry. So in the sense that
okay.
yeah. So it's so non-degenerate CR. So okay. So the group would be,
and this is a type of parabolic geometry, I guess.
Yeah. Oh yes, very much. So yeah. So the main group is SUMM, and then you the stabilizer. So P, where P would be the stabilizer of a. So you can think of it. Okay, so if you have this homogeneous model, P is the stabilizer of a complex null direction, where null is defined with respect to a sorry, this is the wrong, to a Hermitian form. So actually it's the wrong, so it's m+1, 1. So you take your vector space, the flat model will be based on the homogeneous space. So it's the projectivization of a null cone defined by the vanishing of a Hermitian form on Cm+2. This is what it means. But I don't want to go into.
No, I understand. Just wanted to see the connection. Okay, thank you.
So I generalized this equation. So on the basis of results by Jakubowicz, I realized that if you change this density, so you can change it in different ways. So first of all, you can allow it to be complex, and then you can allow it to have a different weight, and you still get conformally invariant differential equations. But these now have an interpretation in terms of the analytic properties of your CR manifold. So first result is that MHJ is realizable as a hypersurface. So this means that there is an embedding of M into Cm+1. And the complex structure J is induced by the complex structure on Cm+1. So if I have such a realizable hypersurface, then I have a solution. So a solution. Now complex solution doesn't have to be real. in general, it will not be real, in fact, to, well, precisely the same equation as I wrote before. But now it's theta being complex. And actually, it works the other way. So this is well, so it's given by so it's a reinterpretation of results by Jakubowicz. And the other one, so the other interpretation I had is it's the existence of two sections of this bundle. So now the weight is different. And one is a solution to this equation, so the same equation as before. But then the other one is given by this equation. So these two results here, so here, let me restate it. So the 2 means that M is realizable as a hypersurface in Cn plus 1 if and only if it admits two solutions, sigma and tau, to these equations. And these equations are CR invariant, you can check. So this is based on Jakubowicz results. And another one that I found is, well, so in this case, you have to work in 3 dimensions only. Then your manifold, your 3-dimensional CR manifold admits a CR function. So this is a function f, which is complex valued, which is annihilated by any section of H01. So this is equivalent to the existence of a pair, nabla alpha. So nabla is actually my Webster connection. And then a 1 form or 0-1 form, lambda, that satisfy this equation. And one can check that this equation here that I'm writing is a nonlinear version of the first equation, actually of either this equation or that equation. And this is based on results by Lewandowski, Hill, and Nurowski. So actually, these equations are very much, well, so I came across the third one here, this one here, while investigating these algebraically special solutions to Einstein equations in dimension 4. Okay. So do you have any questions? If not, I will proceed.
Yeah, so I have a question. Do you hear me here?
Yeah, I can hear you.
Right. Formally, I don't understand the second condition because I think that one can choose always sigma. I think that sigma can be 0 if epsilon, if E1, if this E11 is a vector bundle, there exists the notion of 0 section and the 0 is a solution. Okay. So I don't know how to circumvent this, maybe.
Yeah, okay. So you assume that it is non-vanishing. But okay. So this is a good point, and I will come back to this later. But as far as the densities on the CR manifold are concerned, in my talk, they will be assumed to be non-vanishing. So you're completely right. So I should put this.
Okay, thank you. And next question, sorry for that. Why do you require in 3 that the Tanaka, Webster, nabla exist? If this nabla A,
So I was not very clear. So in fact, so I claim that this is CR invariant. So what I mean by this, it's actually part of an equivalence class.
Mm-hmm. Yeah.
So maybe it will answer your question. So by this, I mean that, you know, if nabla hat is a different Webster-Tanaka connection, as I wrote it before, then lambda alpha has to transform in this way. I mean, it's a very good point that you raised. I guess this is what you wanted to say.
So there exists a Tanaka-Webster connection in the projective class of Tanaka-Webster connection such that nabla lambda b with these hats is
actually, okay, so it should be, so it's independent of the choice of Webster-Tanaka connection. But so if you have one solution like this, so fix a Webster-Tanaka connection. If you find a solution lambda, then if you change your Webster-Tanaka connection, then lambda has to transform in this way.
Yes.
So actually, just to make it clear. Yeah, okay. But actually, maybe I can put, I mean, if you want to show the equivalence of one, or rather not the equivalence, but if you want to see how one implies 3, then you put lambda alpha is equal to I theta inverse nabla alpha theta. And because theta has this weight, actually you could take even this weight, then you'll see it will transform in this way. So in fact, the equation in 3 is more general. It's non-linear, but it's more general than the one in 1. So this is why I call it a non-linear version of this Webster connection.
Thank you. I think I have it sufficiently explained there. So thanks.
Okay. Okay, so let me carry on with conformal geometry. So I think it's probably two conformal geometry. I'll be very quick because I think I'm running out of time. Conformal geometry. So, okay, so I'll be very quick. So for us, a conformal manifold, well, so it consists of a manifold M and C. So C is an equivalence class of metrics related in the following way. So they're conformally related, okay? And so if you take the Levi-Civita connections of these metrics, they're also related in a funny way, actually in a simpler way than the Webster-Tanaka connections would be. But I can use the shorthand, the same shorthand as before. So actually conformal geometry and CR geometry, contact CR geometry are very similar. And similarly, I can introduce density bundles. And these have only one weight. So they're parameterized by these W, which are real numbers. And the interpretation is, well, so I can add a little plus here, meaning that the densities are positive. So if I take a section of one of these density bundles of weight 1, then I can produce a metric, so G. So I get a one correspondence between this theta, so these sections of this main bundle and a metric in the conformal class. Okay, so I don't think I have much time to go through this. I don't want to give too many details, but ask me if it's a bit mysterious to you.
By the way, Arman, you have 20 minutes.
Yeah, but still.
Okay, yeah.
I'm a bit worried. Okay, maybe I can tell you a little bit more. So on a conformal manifold, there is no preferred metric, but you have a so-called conformal metric, which is a weighted metric. So I will underline it like this. And this is a section. So it's this section of this bundle. So this is the symmetric power of the cotangent bundle, and it has weight 1. So if I want to produce my G here, then I take my section here, and I take a power of -2, and I multiply it by this conformal metric. And I can go the other way. So this is how the one-to-one correspondence works. So what's the advantage of using this formalism? So an example, actually it's an important application. So if I want to find a metric, an Einstein metric, G in C, then the corresponding section, sigma, has to satisfy the conformally invariant differential equation given as follows. So the little circle means trace free. And here, this is so this is rho, and it's meant to be the Schouten tensor. And as you will probably know, the Schouten tensor is a trace-adjusted version of the Ricci tensor. So if I find a solution to this equation, so here actually an important point is that sigma is not 0. So sigma is in this bundle. So if I find a solution to this equation, then I get a global Einstein metric. So this equation actually is due to Lebrun. But then Roth-Gover had an absolutely brilliant idea. So that was in 2005. So he allowed sigma to be a section of this bundle, i.e. sigma may have a 0 set. 0 set. And typically, I mean, why is it a brilliant idea? Well, so first, you do not get global Einstein metrics, and you might wonder what happens on the 0 set. And you can interpret this 0 set as some kind of conformal infinity. If it is non-empty, of course, conformal infinity. If it is a hypersurface, yeah. So we'll come back to this later. So in this case, Roth-Gover called sigma an almost Einstein scale. So it's Einstein scale because it defines an Einstein metric, and almost because it fails to be an Einstein metric on the 0 set of this section. So this is an absolutely crucial point of what I'll be talking about later. Okay, so that's it for conformal geometry. Next, I want to talk about so-called optical geometries. So I will start with a definition because it's less well known. So it's motivated by general relativity. So you start with a conformal manifold. So I will put tildes for reasons that will become apparent later. So I start with a conformal manifold of dimension 4. And I join to it a null vector field K. And so this is called an optical geometry. So this is really terminology harking back to, I don't know, probably Trautman introduced this terminology. And I will impose, okay, so you have a null vector field K here. And so you have a foliation of your manifold by the integral curves of K. And this is called a twisting, non-shearing congruence of null geodesics. if, so if K satisfies the following equations, so by non-shearing, it simply means that if I take the lead derivative of any metric in a conformal class, but I restrict myself to directions that are orthogonal to K, then I get the metric back up to a conformal factor. So this is, so rho is a function on the manifold, and V is in the orthogonal complement of K. So this is non-shearing, and actually it's non-shearing on all geodesics. So the curves are necessarily geodesics. The integral curves are necessarily geodesics. And twisting simply means that kappa wedge d kappa is non-zero, and this kappa here is simply G of K, like this. So it's the one form associated to K. Now, these conditions are conformally invariant. And in fact, I could rescale K and I would get the same conditions, but I will tell you something a little bit more about this later. One interesting point that is particularly useful, so I'll call it a fact. So you can see this fact in Fino, Leisner, and myself in a recent article, maybe 2021, I forgot, maybe 22. So there exists a conformal subclass, let's call it C and E, such that for any metric in this subclass, L, K, G, V is actually zero. So this function here is actually zero. So it actually determines a conformal subclass. So why NE? So NE means non-expanding. So this is, again, terminology from general relativity. The congruence is non-expanding in this case. And the good thing is we can write G tilde uniquely as 4 theta symmetric power of lambda tilde plus 2h alpha beta. So alpha and beta here run from 1 to 1. So it's got only one index, one value. But I'm doing this on purpose to make contact with what I said before. So what is theta? So first of all, I should say that 2 theta is equal to K inserted into G. So it's the dual of, so this is what I called kappa before, or at least half kappa. And this theta is a contact form on the leaf space. So maybe I should say. On the leaf space of the congruence. And this is actually a CR manifold, a contact CR manifold. So the leaf space is a CR manifold. So the space of all null geodesics of this congruence. So this is K is the congruence. And d theta is exactly what I wrote before in terms of my adapted coframe. So basically what I had is I can express my metric G tilde in terms of an adapted coframe for the CR leaf space of the congruence, and then this lambda tilde is uniquely determined. This is one form, so lambda tilde is a unique one form dual to K. Okay. So the point is the fact that I have a twisting non-sharing congruence of null geodesics allows me to conclude that the leaf space of the congruence is precisely a contact manifold of dimension 3.
Okay. Sorry, Arman. At least to me, it's not clear at this point.
It's probably not clear because I went quite
the CR
fast.
Structures are.
Yeah. Okay. So in fact, if I go back to this definition here, where is it? Oh, here. Mm-hmm. This tells me that. Sorry, let me use right now. So if I take, K is a vector field, a null vector field. Mm-hmm. I take its orthogonal complement, so it has rank 3. Then I quotient it. Because K is null, it contains K perp. So I can take the quotient of K perp with K, and this has rank 2. Okay, mm-hmm. And this condition tells me that the conformal structure restricted to this bundle, so this is called the screen bundle, is preserved along the flow of K, and so it must descend to the leaf space of the congruence. Mm-hmm. And now, so this is one condition, but this, as I said, implied that the geodesics are, the curves of K are geodesics, and I can re-express this as taking the Lie derivative of kappa, this kappa here, along K, and this is proportional to kappa. So it means that I have this one form that descends to the leaf space. Mm-hmm. And this, so I can identify this screen bundle to a rank 2 distribution on the leaf space. Now, this condition here tells me that there is also a sub-conformal structure on this rank 2 bundle on the leaf space. So it means that, so what I called H before can be identified with this bundle. And the subconformal structure coming from this property gives me a complex structure for free. So this is how it works. I hope.
So maybe this is the part I don't see. So what is J? How is it related to the conformal structure?
Okay, because the H is of rank 2 on a rank 2 bundle, conformal structure is equivalent to a complex structure. I mean,
okay, so there's some general well-known relationship that you can use here.
Yeah.
Okay, all right, okay, that's fine.
Yep.
Thank you.
So so another way of looking at it is that, so I don't have that much time actually to explain all this. So maybe you can
it's all right. Later. I can ask later.
Because I'm a bit worried that I'm running out of time.
Yeah, so please continue.
Okay, so another point is that this generator K is unique. I mean, I could say unique up to sign, but I am assuming that my manifold is oriented and so on. So it's essentially unique. Okay, so what does it have to do with the Fefferman construction? Well, the Fefferman construction is a special case of these non-sharing congruences of null geodesics. So conform the Fefferman construction. So I'll have to be very, very quick. So in this case, so it's a special case. So you start with your CR manifold. Let's say it's your CR threefold, it's contact. Then you have this canonical, well, so then I will not use the canonical bundle, but the power of it. So you have this bundle here. you remove the zero section. So this is a C star bundle. And then you take the quotient by the natural action by non-zero R. So this is a circle bundle. And this is referred to as the Fefferman bundle. Okay, so this is the Fefferman bundle. And this Fefferman bundle is equipped with, well, first Fefferman metrics. So let me tell you how you proceed. So first you want to trivialize this bundle, which I'll call M tilde. You trivialize M tilde by choosing a section sigma of this bundle here. It's got CR weight 1, 0. So this defines a contact form. There is a contact form associated to it. So it's roughly sigma bar. So, okay, so I'll use shorthand. And it also defines a fiber coordinates on M. And I'll call this fiber phi. So I have these ingredients, and then what I can do is define a Fefferman metric. And this is given, so it really depends only on the contact form, theta here. And it's defined in the following way. So it's a bit fancy. Actually, maybe I should refer to the work of Fefferman, Lee, Gover. Actually, I take this form from a paper by Chap and Gover. So this tensor here is the Schouten tensor of the Webster connection, which I didn't really talk about. And so you see that it has exactly the same form as one of the metrics I considered before. So 4 theta lambda tilde plus this guy here. So the second term is what I wrote by H here. I express it by H. So this guy here, this lambda tilde is a particular example of one of the geometries I mentioned earlier. Now, of course, so if you change, so it does not depend on the choice of sigma. You can check this, but if you change contact forms, so then G associated to the new contact form is rescaled. So what you get, in fact, is not a Fefferman metric, but a Fefferman conformal structure. So this is how it works. So this is the metric, and this is the Fefferman conformal structure. So here, theta is related, theta hat is related to theta by this formula. Okay, so in this case, the vector field K is conformal killing. So this is a special case, well, is a special case of what I mentioned before. Because if it's conformal killing, then in particular, it's tangent to a non-shearing congruence of null geodesics. But the converse is not true. So okay, so where's my, okay. So you have a twisting, non-shearing congruence of null geodesics. But the converse is not true in general. So a solution is to perturb the conformal structure, Fefferman conformal structure, by a semi-basic form So this is a one form on the Fefferman bundle, such that if you insert k into it, it is 0. Okay? So if you do this, then k is no longer a conformal killing. So you start with your Fefferman conformal structure, and you perturb it in this way. So a Fefferman metric, perturbed Fefferman metric will be defined to be conformal, so Fefferman metric plus the additional term given in this way. So theta is the contact form, and this xi tilde is this one form that depends non-trivially on the fibers of the vibration. So this is the perturbed Fefferman metric, and it gives rise to a perturbed Fefferman conformal structure. So this is perturbed Fefferman metric. Okay, so okay, maybe I should cut along. So how much time do I have? I think I've run out of time, but it's
yeah, but I mean, if you need a few minutes to finish, it's fine.
Yeah, I still have quite a bit. But okay, so let me try to summarize. So I still have two main results to present, so this is why I'm a bit worried. So this perturbation one form can be Fourier expanded, because you live on a circle bundle. Expanded. And the coefficients can be suitably interpreted in terms of what I call CR data. So that is CR densities, so CR data. So these are CR densities of various weights. So if you add this semi-basic one form, you add further data on your CR manifold. So this perturbed Fefferman structure depends on additional data coming from the base space. And then if you impose differential conditions on, let's say, on the existence of a particular Fefferman metric, a perturbed Fefferman metric, then it will be translated into CR invariant differential equations on your CR data. So, okay, so maybe I should say, so you can express this CR data as a tuple. So I'll be very quick and hand wavy. So this will roughly corresponds to the coefficients, but they're actually densities. There's a complicated story behind this. And I and J's are just subsets. So I is a subset of Z, and J here is a subset of Z negative. So this is the CR data. So okay, so there is so you should think of them as the Fourier coefficients of this semi-basic one form. Okay, so now let me give you one result. So this is what I call theorem B. So this is new. So if I start with an optical geometry, so M prime, C prime, K prime, so the leaf space will be a CR threefold. So optical geometry with a non-sharing congruence of null geodesics, which is twisting. Now, assume that the Weyl tensor and the bar tensor of the conformal structure here satisfy these properties. So these two properties. So V here, again, is in the orthogonal complement of K. Then M tilde prime is locally, conformally isometric to a perturbed Fefferman space. And the perturbation one form of this Fefferman space has the form, so it's given by some CR data. So it depends, so it has only two non-vanishing coefficients in this 1, 0 part, and then it's for the remaining part, it has three coefficients. Sorry, I messed up. Okay, I'm very hand wavy about the notation. But the point is, I mean, the main part is that really, if you have these two conditions on your non-sharing congruence of null geodesics, so these are conformally invariant conditions, then you can deduce immediately that you're locally on the perturbed Fefferman space. So if you're on the perturbed Fefferman space, okay, and you also know the form of the CR data, but the point is that if you're on this Fefferman space, you can use all the machinery that is available concerning the Fefferman construction. So this is an advantage, and it makes things a lot more tight. Okay. So this condition here tells you that you get these two coefficients here, whereas this condition here tells you that you have these three coefficients here. Okay, and then, so this is theorem C, and I'll end with this. So if you have a Fefferman space, perturbed Fefferman space, so I'll write it down like this. The perturbed Fefferman space, as in theorem B. So it has this CR data here. So what can you do with this CR data? Well, so first, what happens on the Fefferman space itself? So we have the following two conditions are equivalent. So following conditions are equivalent. So if it admits what I call the almost pure radiation scale, so this is a conformal scale of weight 1, such that, so by definition, it satisfies a differential equation of this form. So it's very similar to the almost Einstein condition, except that you have an additional tensor here. And this tensor here satisfies an algebraic condition, which is this one. And kappa here is G of K. And there is some additional condition, which is given by this guy here. Sigma tilde, so there's tilde, plus 2 phi A. Yeah, so I have this condition. So if I have a pure radiation scale on my manifold, my Fefferman manifold, then the CR data, so the CR data is constrained. And in particular, and in addition, I should say, and there exists a density, sigma, a CR density of weight 1, 0, such that, so I'll have to be brief here, such that sigma satisfies this condition here. So it's very similar to one of the CR invariant equations I wrote before, except that I replaced this Webster connection by a gauged Webster connection. And the gauge one form is precisely given by this guy here. So this is what I had. And there is an additional condition, which is a bit more complicated. Sorry, there is no tilde here. So this density here satisfies this property. So I have to be extremely quick to wrap it up. Nu alpha minus 2i alpha minus 2 0 is equal to 0. Okay, so I have these two conditions. This nu alpha is simply this guy here. And these two conditions here, if you refer to what I said before by theorem A, I mean, actually it's a variant of theorem A, it tells you that the CR manifold is realizable as a hypersurface. So I'm actually making contact with results by Tafel, Lewandowski, Nurovsky, and Hill. Okay, so I had other results to present, but I'm mostly done, and maybe I should finish now, and you can ask me questions because I've run out of time. Okay, thank you.
Okay, let's thank Arman for the very nice talk. Okay, so now we have some time for questions.
Yeah, you mentioned, if I may,
yeah.
Arman, you mentioned these Fourier coefficient expansions. Isn't it motivated by the results from 2001? I refreshed my memory of Graham and Zworsky on the regularization of the volume. They also uses some expansions connected to Fefferman formulas.
Oh, really? Okay, I didn't know. I mean, if you can send me a reference, that would be nice. Because I thought this was the obvious thing to do. And in fact, I know that, for instance, Lewandowski had the idea of doing this many years ago. Yeah, so I wasn't quite sure. So was Graham's work related to some kind of perturbation in the same sense?
It was purely conformal and Einstein. It was not CR.
But surely it should be related to CR geometry because...
yeah, as you mentioned, yeah. But they also had some logarithmical parts in these expansions, not really powers x to the alpha or
but are you sure?
But they have also, I just was curious in the sense whether it's connected.
Yeah, but it might be something else. It might be the Fefferman-Graham ambient metric.
Probably only this, yeah. So it's other Fourier.
Because the Fefferman-Graham, yeah, because the Fefferman-Graham metric will involve these kinds of expansions, but they were not really Fourier expansions. But maybe they did something, and
it depends. No, okay. Okay, thank you. Thanks.
Thank you.
So maybe I can ask. So there are many kind of steps in your construction, and I was wondering about the role of topology, because almost everywhere you're dealing with just differential equations, which are local, except when you do take some Fourier expansions. So
actually, it's all local, and the Fourier expansion is only with respect to the fibers that are But so actually, a lot of things will fail on the global level.
Okay, but I just wanted to make sure I understand. So this Fefferman bundle is so you start with three-dimensional CR manifold, then you make this circle bundle. Now it's four-dimensional. Now a metric and this null vector field, which now you can interpret this as a Lorentzian geometry, right? Yeah.
Well, actually, it's conformal because.
Okay, but what is the role of the circle topology with respect to the Lorentz structure? So
so the bundle is well, we don't know much about the topology actually. So we make the assumption that this bundle exists. So we have this canonical bundle on the CR manifold. So it's the top power of the annihilator of H01, and then well, we assume that we can actually take a root of this bundle. So it's a line bundle, and we assume that we can take a root of this bundle. So already we're making an assumption. So it might not necessarily, this root might not necessarily exist.
I mean, even local, you have these circle fibers. So I was just wondering if these circle fibers could give rise to closed time-like or closed null curves in the Lorentzian geometry, or that's somehow excluded by your construction.
Well, okay. So these fibers are the null geodesics.
So they are closed null geodesics.
Yeah. So they're but no, they are not closed. So this is the point actually, in the sense that yes, in a sense they are closed. You identify them, So the example with the Einstein metric, or the almost Einstein metric, or what I call the almost pure radiation scale, is actually this is what I wanted to talk about later. So they typically have a zero set. They always have a zero set actually, which you can identify as the conformal infinity. So you have this hypersurface, which you identified as a section of your Fefferman bundle.
I see. Okay, so it's the section splits the circles so that.
Actually, you have two such sections. And they're related. You can express these sections expresses.
Okay. Okay. Interesting.
Yeah. So it does not really. So you're still tied to these congruences of null geodesics. So for instance, with this pure radiation scale, you can show that the metric it defines is asymptotically conformally flat, and in fact either conformally anti-de Sitter or de Sitter or flat. Only along the directions of the geodesics. So a good example where it would fail globally is the so-called Taub-Knot ADS metric, which is known to be globally non-asymptotically flat, or de Sitter, and so on. So it's only in certain directions. So there are issues with topology, but at least locally we get a good grasp of what's going on.
Okay, very good. Any other questions?
Maybe if you can say us, Arman, about the role of a possible allowance of the zeros of these sigmas. You spoke about Gover, who allowed sigma to be 0. So
yeah.
you know, one can invert sigma, or I remember this. Yeah.
But you mean the CR side or the conformal side?
The CR side.
For the CR, I don't know much about the CR side, to be honest. Yeah, but in this case, okay, maybe I should emphasize this in this theorem that I presented here. So maybe I should add it. I don't know if it still shows. This is always non-zero.
Mm-hmm.
Yeah, so there is no issue with the zero set of this one. Yeah. But it has to be non-zero because it's the scale you use to define the Fefferman metric.
Mm-hmm.
So the zero set is only affects this guy here. So this has a zero set.
Mm-hmm.
So this must have a zero set.
Does it say something for the? Does it say something for the gravity when you speak about the conformal side? For the gravitation, this possible zeros of sigma.
Yeah. So this is what I was just mentioning. You identify the zero set as the conformal infinity of your manifold, but only along the congruence, only along the foliation of the tangent to K.
Yes, okay. Mm-hmm.
Yeah, so in fact, you can also take the Fourier expansion of the Weyl tensor and derive a number of properties regarding Petrov types and so on. Yeah. So there is quite...
It's not connected directly to the shearing of geodesics and to these naive things, or not in the sense you mentioned.
Well, you assume that you have one non-shearing congruence.
Yeah.
Yeah, so this is the basis for this. But then the point is you can derive additional conditions on the CR data.
Mm-hmm. Yes, thanks.
Okay, so maybe there are no more other questions. So let's thank Arman again.
Okay, thank you very much.